from a distant beginning to an even more distant end. And we weren't there when it started, we won't be there when it ends. Okay, well, I'll give you a few slides here, and there's all kinds of things going on, of course. Oh, okay.
Do you want to stand? If you stand back.
Maybe I can do here, and then I can copy both.
Okay.
But mostly I'll be looking at the slides because I'm moving them through and so on. And I guess this, okay. This is Brian Greene. Our human moment of thought, our instant of light, is at once rare, wondrous, and precious. And when you think about it, you understand that people only got started in the world. Our world, as you'll see, only got started fairly recently compared to the time of the universe that we're aware of. Oh, there we go. There's a whole bunch of books. We have a wonderful library that has so many books. The one I have here, Before the Big Bang Outline, that's one I would recommend if you're not going to read all of them. So that's one to take a look at if you're interested in following up on this. The science about the origin and the end of the universe is unsettled science. No ideas about these topics are final because we're always learning more. As time goes on, we get more information. We expand our knowledge of the universe, and that changes our view at least slightly about what was happening and what's going on. I keep getting.
There we go.
Alternatives abound, and there are inconsistencies because a lot of it is interpretation. There's no final result on all of this. There are subtleties everywhere, and of course that makes the science more difficult. And different people interpret the subtleties differently. I get the light, but I guess I'm just not. Oh, you did that though.
No, I didn't.
Oh, okay.
You got the right
There are
one.
about 65 billion neutrinos from the sun passing through your thumbnail every second. Where's the sun down there? But of course, there's very, 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 very little interaction with anything, which of course makes it very difficult to study neutrinos. So you have to have a huge detector and wait a long time and be very sensitive. Okay, here we go. From a recent television discussion, Roger Penrose, who is one of the gurus in Britain about physics, and he's written a lot, he has quite a reputation. Time has no beginning, and the Big Bang is wrong. So we're walking on thin ice here when we're talking about this stuff this evening. I don't know. Time has no beginning sounds reasonable to me, but what was before that? I don't know. She also has written some things very understandable and comprehensible. This book, Existential Physics, was good. Before the Big Bang is another one. Marcini Houghton is quite a knowledgeable person in this area, and she's also written books. These are all books that are available in the library if you're interested. That is the Downtown Physics Library. Almost everything we know about the universe is from photons we see here on Earth. Photons of different wavelengths, of course, are radio waves, X-rays, gamma rays. We use them all. The Doppler effect allows us to measure the Doppler effect of these waves, allows us to measure whether the stuff is moving away from us or coming toward us. So we get a lot of information from that. Each second, about 65 billion solar neutrinos pass through every square centimeter of Earth. So over there through my thumbnail, every second, fortunately, they don't interact very strongly with me. We know 4 fundamental forces: gravity, electromagnetism, strong nuclear force, and the weak nuclear force. And these have a lot of subtle interactions and interactions with each other and the things that we see around us. String theory would lead to all particles being just different aspects of vibrating strings. Of course, these strings are so minute, you don't really see them. Smaller than an atomic nucleus, we can see protons and neutrons, but they are, according to this, just representations of vibrating springs that are even much, much smaller than that. So that's still up for grabs, whether that really is serious or not, but it's something that's out there and is always presented. This Hubble ultra deep south is just absolutely incredible. The Hubble telescope going up has provided such a wealth of information and pretty pictures that we can really appreciate it. And they're getting an awful lot of science and they expect to get a lot more science. New James Webb Telescope images suggest our understanding of the cosmos is flawed. If that result is correct, we might need new physics to explain the universe, not just new ideas about the present physics, but actually new physics. That would be kind of neat. Oops, I keep not doing it far enough. Of course, that's the James Webb Telescope. And actually, I think I was in this room watching that all happen whenever it was being put up. Yeah, well, since Galileo discovered the universe in 1610, he didn't really discover the universe, of course, but things have become a lot more complicated. And of course, we know an awful lot more about it. So it's rather more satisfying in understanding what we do understand. And the challenge is to learn even more. Whether we'll ever get to the end of having a complete standing, it's really hard to know. But whether you're talking about quantum mechanics or space warps, artificial intelligence, dark matter, neutron stars, multiple universes, maybe, just all kinds of stuff, it's really hard to know. According to Einstein's equations, gravity can also be repulsive. The Big Bang was really fast, like that, even faster, really. But it was really fast. And Alan Guth, in the December of 1979, and I still remember this became big news in the science community at the time. He realized that a region perhaps 10 to the minus 27 meters across could expand explosively due to a force called the inflaton field. And there's no I in inflaton field. Hydrogen is about 10 to the minus 9 meters. You can see the region that is projected as being the smallest start of our universe was much smaller than that. Cooling as it expanded, the material clumped into stars, planets, and miscellaneous debris scattered across space, creating our universe. This is Alan Guth, Mr. Big Bang, Mr. Inflation. Back in 1980, he was an MIT student. And I remember whenever this first came out, and he was giving talks on this, and it was kind of an exciting time. Talks of Guth discussing these ideas can easily be found online if you want to go and see some of the talks given by him. He's talking about other things also, not just this. Alan Guth's office at MIT. He's a proud winner of the 2005 contest for the messiest office. I show this to my wife once in a while, but a galaxy similar to our Milky Way galaxy. These spiral arms, just absolutely amazing. Our solar system orbits the center of our galaxy at about 537,000 miles per hour. Really fast. But of course, you don't notice it. And things are so far away that you don't notice things in the sky changing very much either. You actually have to be very careful in tracking it. You can see, if you're very careful and look over time, you can in fact see things moving in the sky, but it takes pretty careful care. Whenever I was an undergraduate, one of the things I did was I took plates at one of the, with one of the telescopes that we had at the college, and you take a plate, photograph, you were told what direction, what stars to look at, and you take a plate, and then you move it over, you take another picture of the same plate, you do 4 one way, turn around, you do 4 the other way. And then some lucky person gets the opportunity to measure each one of those compared to the standard stars. Not my task, thank you. But it was slow and painful work. But on the other hand, it was able to tell proper motion of a lot of the stars, which was under study at the time. And we learned a lot about things of that sort. The distances are absolutely huge. Our solar system, if our solar system is a quarter, the galaxy would be the size of North America. I mean, just amazing the way things scale up. If our sun is a quarter, the nearest star is 400 miles away. If our galaxy is the size of a quarter, the nearest galaxy is only 1.5 feet away, okay? Now within this, big spaces, but so when you consider that the big spaces must be in here, although it's only in terms of the galaxy size, 1.5 feet away, that 1.5 in the real world that you and I know about is huge. So the things really are quite significant. If the age of the universe is 13.799 billion years old, let's lay out a framework here to see how things fit into the whole gizmo here. And this is our present time at 13.8. Let's take a look at when the universe begins. And space expands at almost infinite speed from nothing. And then we carry on from there. And the idea is that nothing existed before us, not even space. That's one of the conjectures or the statements that in some of those books that I pointed out to you earlier. I can't wrap my head around that, but that's where it goes. Star formation started pretty early. Once these things blew up, and then things start to clump together here and start to clump together there and start to clump together here. Heavy elements, neutron star mergers from higher isotopes limit the causes of expansion. Now, whenever you had star formation, you basically had just hydrogen and helium and a couple of other small elements like that. And then gravity would pull these things together. And they would finally get together, and finally they get so much stuff and there'd be so much gravitational energy and slamming and so on, that a star would actually form. And after that star formed, it would use this hydrogen into helium, into higher elements up to about not more than iron, mostly just into the 12, 13, 14 number elements. And then it would run out of the ability to make more energy, and the whole thing would finally collapse. And that collapse would create an explosion that created all of the other elements that we have, the higher elements above iron. That's how they became apparent. Planet formation, then, again, this stuff is scattered through the universe, and then different parts of it clump. Some clumps into a star, and then you would have other stuff clumping around it that would become planets of different types. We look in our solar system, we see several different types of planets. So you get different things. And then after a while, you have all the elements there, and life starts to form. Initially just small, simple life, of course. And then finally we have people, intelligent life. And then we finally end up with the present time of life on Earth. And we know that in a few billion years, our sun will explode. We don't have to worry about that. And so there has been, whoops, I think I pushed the wrong one here. Yeah. Okay. And then possible intelligent life was about 9 billion years before us. Maybe it's some other planet, it's some other star. It just got started before our star and planet system got started. Intelligent life. That's a long distance between here and there. So we don't know about them. As far as we know, they don't know about us. Maybe they're just studying us. About 4.54 billion years from when our sun started until now. And are there UFOs? And I always worry a little bit about putting that in because it's a little bit doo-doo-dee-doo. But on the other hand, there's enough time for there to be intelligent life out there. And we don't have any way in a reasonable time to get any long distance. But if you think back to 1850, when the wagon trains were headed west, they had no idea. They thought it was pretty fast whenever you would put, you get messages from the East Coast to the West Coast by getting it out by train for a while, and then you put it on horseback rider and you go pretty quickly. They had no idea about trains, and they certainly had no idea about radio waves. Radio waves didn't come in to knowledge until 1865 or something like that, 15, 20 years later. So there may be some technology out there that we don't know about, or maybe not. I don't expect to be talking to any aliens, but the thing is, it's hard to just throw it off and say that it's not a possibility. After 100 trillion years into the future, star formation ceases. as far as we can tell. Possible fate of the cosmos could be the big crunch that everything gravitationally starts coming back together again and crunches. Things could get hot in some way by having some additional things kick in. We could have a big rip. We don't really understand space well enough to be able to say that it isn't going to get ripped apart somehow, vacuum decay, or a balance. Maybe it'll all come back together and will explode again into the next version of universe. That maybe that's where we came from. That's all up in the air. We don't really understand a lot about that kind of stuff. Earlier this year, you've probably watched at least some of this on television if you have any interest in this stuff at all. This is the UFO meeting. NASA hosted an unidentified anomalous phenomena meeting. And it was kind of fun to watch a UFO meeting. And you can still get all of this on YouTube if you're interested. And here's the address. So just that you know to look for it if you're interested, you can go and find all of this stuff. Of course, our astronaut Senator Mark Kelly was one of the participants in this. He didn't really say much, except that sometimes you're flying around and you see something unusual goes whizzing past, and you don't know what it is. Maybe you turn around and go see it, and it's just a balloon or something, no exciting thing, not a UFO, not something from another planet. So he put in his 2 cents, and they at least had this big discussion about all of that. On the other hand, you've probably seen this picture. It's on the internet all the time if you're looking at this stuff at all. We don't know what it is. It moves very fast, about 40 feet above the water. And it's not our task to determine what the object is. Now, one of my friends has suggested that it's perhaps some secret kind of, these are public kind of pictures. These are everywhere, okay, if you really go looking. One of my friends suggested that maybe it's a secret kind of thing, and they really just don't want to tell anything about it. And they did go into a private session to talk about this more. So it could be that they shared with the other people on the committee, but they weren't going to tell the public because they don't want to spread information about it around. Okay, the life cycle of our sun. Things start, this stuff accumulating and coming together, and finally it fires on and gets some of the nuclear reactions going. And it will continue. Whoops, I don't want that. I guess here we go. It'll continue along. Here's where we are now. And it'll continue pretty much like this for quite a long time, billions of years. And then finally, it also will burn itself out and collapse and have a big explosion, end up with maybe a white dwarf. Let me give you a timeline of our universe again in another way. We don't know what happened or how our universe started, but perhaps this is one way that it could have started. It's cyclical. It'll go up, then it'll crash and come back, and we're in the middle of one of these things. We don't know what. Maybe that's a realistic interpretation. Perhaps it's not, but it's one way to look at it. Perhaps there are more surprises in our future. Here's something that was really kind of surprising. This is from the James Webb Telescope. I'm sorry, this is Palomar. In 1952, the observatory observed a close grouping of 3 point-like sources measuring 15th magnitude and brightness. It took another image an hour later, and 3 objects had vanished. Follow-up observations scanned the area down to 21st magnitude, and they were still missing. Now astronomers have used a 10.4 meter telescope in the Canaries, which should have seen anything brighter than a 25.5 magnitude, still nothing. What were they? Where did they go? The UFOs? Nobody really knows what's going on here. We know a lot, we still have a lot to learn. Where did it all come from? We really don't know. What's out there whose existence we're still unaware of? As we go to look at other stars and planets around other stars and so on, will we find other life? Will we find other interesting kinds of things that we haven't been aware of so far? Maybe there are more surprises in our future. Let me walk through just quickly. How did our universe begin? this is what we do know. There's a big bang. This was taken out of National Geographic a couple of years ago. The Planck epoch, this happened in a period which lasted only 10 to minus 43 seconds, is not known. Shortly afterward, the inflationary period started. So what really happened in that initial zip to get everything started, we really don't understand what's going on with that. 13.8 billion years ago, our entire visible universe was contained in an unimaginably hot, dense point, a billionth the size of a nuclear particle. Since then, it has expanded a lot and fighting gravity all the way. Inflation in far less than a nanosecond, a repulsive energy field inflates space to visible size and fills it with a soup of subatomic particles called quarks. Protons and neutrons are all made up of different types of quarks. The universe expanded by a factor of at least 10 to the 26 during inflation. It expands, cools, quarks clump into protons and neutrons, the building blocks of our atomic nuclei, and perhaps dark matter forms. We'll talk a little more about dark matter in the future and a little bit later. But we don't really understand dark matter either, but it's everywhere, it's pervasive, and it has its influence. The first nuclei universe contains to cool, the lightest nuclei of hydrogen and helium arise. A thick fog of particles blocks all light. And this is still very, very early in our universe, just in milliseconds, trillionths of the present size. First atoms, first light, as electrons begin orbiting nuclei, creating atoms, the glow from our infinite universe is unveiled. This light is far back as our instruments can see, 380,000 years. That is, with all of these protons and electrons bouncing around, that interferes with any light going anywhere. So you can't have a beam that goes from here to the hallway without it interacting with a whole bunch of positively charged particles and scattering off and so on. So we can't look back beyond this time. Everything is hidden from us previous to that time. The dark ages, for 300 million years, this cosmic background radiation is the only light. Then clumps of matter start to become galaxies and start to glow brightest. That is, stars are formed and they clump into galaxies, and that's when we're getting that kind of material. Gravity pulls the first stars, dense gas clouds together, and all the dark matter collapse under their own gravity to eventually form stars and galaxies. Nuclear fusion lights up the stars. That's at 300 million years. Whoops. Did I go backwards somehow? Oh. Let me walk through this quickly. Well, okay, no, we'll go with this. That's a Hubble deep field photo. It just boggles the mind, the amount of stuff that's there. And the more they blow it up, as long as there's enough light intensity to get a little bit of indication of something being there, there's something interesting variety of stuff everywhere. A patch of sky the same size as a tennis ball placed at the other end of a football field. So it's a pretty small part of the sky, and yet it's filled with this kind of stuff. A variety of things out there. This James Webb exposure took just 12.5 hours. The smaller Hubble telescope would have taken weeks for the same photo. And as you can see, there's just all kinds of variety of things. And these are all taken. Here's 2. Okay, this is 2, 3. Okay, so it's just from this little part of space here. Over here is number 1, which is this one. But there's in this picture that you can't really see the detail. If you blow it up and you have good enough resolution and enough light collected by these huge mirrors, that's why you want these big telescopes to be able to get things like this. And the telescope lens or mirror has to be really good in order to be able to keep the resolution so that you can see more than just a spot of light, but have some structure to it. A recent report indicates there are rogue planets everywhere. That is, planets unattached to a star, and they roam the galaxy, trillions of them. And that's just a recent report. Where did everything come from? Here's what we know. After the Big Bang, there were only elementary particles. These could combine to create elementary atoms like hydrogen and helium and up to iron. When you put hydrogen into, make it into helium, you get energy out. And you keep getting energy out as long as you get up to iron. Once you get to iron, to make the elements higher than that, you have to start putting energy into this. So you really need to have some big bang in order to be able to have the energy there to collapse back into these higher elements. Elementary particles, and you create the elementary atoms. Above iron to uranium, energy has to be added. The energy, for instance, from exploding stars. So the higher elements are created whenever the stars explode and have a lot of extra energy around, and then these things get together and form the higher elements. Elements lowest way to highest, we get energy out. I'm repeating myself here, but another thing, multiple universes, we don't know. Maybe there's some fourth dimension that we can go to that we are not aware of. This is one suggestion that has been made about multiple universes that exist in parallel, and maybe they're going through each other is what creates the Big Bang. We really don't know. And that's not necessarily one of our three dimensions, but some other dimension that we're not aware of. Multiple universes. Is our universe one of these condensations? Are there other types of universes? We don't really know about that either. Big bangs, maybe, these different things. This is all conjecture, just things that people show out there. Maybe something that somebody will try to take a look at sometime in the future when they have the capability and there's enough knowledge base to understand these things without interference from things that we don't understand. Some of the tools we use to study the universe. These are satellites that were put up. I still remember whenever they were putting up some of these, like in 93 and 210 and 213, and the higher resolution they get so that they were able to see more and more. And of course, when they put the satellites up, they look everywhere. They look all the way around, not just in one part of the sky, because they can do that. But they have to be very low temperature to be able to get this kind of a picture. Temperature resolution here in this picture are 2/1,000,000 of a degree. So when they're looking out into the universe, that's what their resolution is, temperature-wise. The size variation of the temperature spots depends upon the presence of dark matter. So it's another window to look at dark matter. It gives another confirmation of the existence and the quantity of dark matter. Not sure how that works, but I'll show you some slides about that in a minute. Found by an automated review of images of the Pinwheel Galaxy, Messier 101, from the nights of August 22nd and 23rd in 2011. You can see on the one side, there's nothing here. And on the other side, you actually have a significant point of light there. Something really has happened, it exploded there. The way that kind of thing happens is this way. You have a star up here, and as it burns its fuel out, it starts to collapse, and then it grows into a red giant. So you have this red giant, and finally the red giant ends up with not having enough energy to keep this outer shell going either. So pretty quickly it collapses, and you end up, this collapses to leave behind a white dwarf, and this blows off in all directions. Now this white dwarf tends to be one size fits all, whether you start with a really big star or a slightly smaller red giant or a bigger red giant, they all come down to pretty much the same kind of catastrophe here, and you leave behind a similar size remnant. And if that happens to be a double star, of which they have lots and lots of double stars out there, the star beside it, this companion, sloughs off stuff, and the gravitational field of this burned out star attracts that. So it's kind of burned out and it's cool compared to a normal star, but it accumulates this stuff in until finally there's so much stuff and weight there that the atomic forces can't hold it back. it suddenly collapses, and you end up with a supernova. Now, because this has been a kind of thing, and you just add a little bit, add a little bit, add a little bit, and the forces of the atomics are pretty much the same everywhere. When this blows up, it's a standard size blow up. So now you've got a standard candle that's really, really bright. So you can look for a heck of a distance and see these things blow up and be really bright. And as I remember, this was discovered by an Australian astronomer who was taking a break, and he went outside and looked up at the sky. And of course, he knew the sky real well. And he said, gee, that spot shouldn't be there. So he's told a lot of the other astronomers, and everybody started looking at that. Several started looking at it. And they started putting all this stuff together and learned about supernova and so on. The standard candle. Collapse to a neutron star or a black hole. Well, while measuring distance with a standard candle, a new supernova, detected from one explosion in addition to the light. In Japan, these are neutrinos now. We're talking about neutrinos, which are really, really very hard to detect. Remember, there's a gazillion of them going through my thumbnail every second from our sun. So they interact very, very rarely. And whenever you make a neutrino detector, you make a huge size thing like the size of this room or much bigger, and you fill it with a liquid that's going to be sensitive to neutrinos interacting with the atoms in it, so that you can get some little bit of light ejected. And then you detect that with a photomultiplier or something. So anyhow, they were able to get 12 detected in Japan's detector. In the IBM facility at Ohio, they got only 8. At the Neutrino Observatory in Russia, it was 5, and a total of 25 neutrinos. But that's really significant in the scheme of things. Let's just take a look at what expansion is. Notice if it's uniformly expanding, then you take a look, here's the central one, and you go to this one and you see a little bit of expansion. Now it's uniform, so the space between this one and this one is the same as the space expansion between this one and this one, but between here and here, this has moved twice as far, but it's in the same amount of time. So the velocity of these things out here, although everything is uniformly expanding, the velocity out here compared to this central thing is much faster. So if we measure the speed, we can tell how far away it is. With uniform expansion, the dimmer they are, the further away they are, and the faster they move away from us, because it took the same amount of time to get further away, they're moving faster. Measuring the expansion rate of the universe. One way is looking at relics of the early universe, such as the leftover light in the cosmic microwave background. Another way is measuring the distances to objects with known intrinsic brightness. That is, if you know, you can recognize now, you studied stars, and you know what brightness certain stars are, and you see one out there and you measure its brightness, you compare that to where it would be if it were this much closer, because you know what kind of star that is. Then you can do the calculation. It's like if you have a street light here and you have a street light on this cross on the hill, you know it's the same kind of street light because you drove past that on the way to the market. Then you can calculate how far that is away by very carefully measuring the amount of light you're getting from it. The first method, looking at the relics of the early universe, such as the leftover light in the cosmic background, gives 67 kilometers per second per megaparsec. And the second method, intrinsic brightness, gives 73. That's outside the limits of accuracy of each of these kinds of measurements. So what's going on? It shows we really don't know even what we think we know. Future studies aided by new equipment, of course. I know maybe several of you were here, maybe whenever we watched them put up the James Webb Space Telescope. I was sitting here with some friends as they were projecting it up here, and it was really kind of neat to watch it play out. And of course, let's see, where am I at here? The sun, our sun is in here, here's Earth, and here's the moon. And this kind of equipment is out here at L2, which is pretty far away, well out beyond the moon. So it's out there, it's isolated, it's cold. It can be shielded very well from sunlight. So you're really back to pretty basic material that you can be studying from that distance at that temperature. The Euclid satellite is positioned at L2. An objective of the Euclid mission is to better understand dark energy and dark matter by accurately measuring the accelerating expansion of the universe. I'm not sure how that does that, but I didn't go into it any more than that. Euclid reached L2 and displayed the first images. These are a couple of the images. Visible light over here and near infrared. And you can see the detail. And you can also see some of these streaks. I'm not sure what those streaks are. I remember watching during one of the eclipses, the amazing number of airplanes and things like that that go over satellites that go over. I have no idea whether that's what this stuff is or not. China to hunt for Earth-like planets with formation flying telescopes. China aims to construct an array of telescopes in deep space to search for habitable planets orbiting other stars. The main objective would be to detect potentially habitable terrestrial planets orbiting sun-like stars in our neighborhood and within the Milky Way. The project is still in the development stage, so they haven't actually put anything up yet. They're still making the plans and putting it all together.
There's more
Any questions?
Acorn's question there.
Thanks for coming. It's fun putting these things together because I learned so darn much. Yeah.